Okay, someone respond. You can unmute yourself and let me know if you can hear me well. Davis, maybe if you're there, unmute such that I can gauge how well you can hear me. You can unmute yourself, anyone. I see Godfrey is trying to say something, right? Okay, Godfrey is saying something. I can't tell. Hmm.
I can hear you.
Yes, I can hear. I think that was Nicholas. Okay, in which case I'm going to get started. In case the audio starts getting bad, you can just let me know in the chat window. Then we can see what to do. Okay, great. So today we are going to be looking at the, the relational model. Right, so I'm guessing you can see my slides. Yeah, I'm at the university, so the network is not so great over here. But we'll see how far we can get with this. So the important thing about the relational model here is it's the most widely used model for representing databases, and it's used by most of the leading vendors. You have your IBMs, Microsoft, Oracle, Sybase, and others. It's also used in legacy systems, older models of databases. But you have some newer models that are coming up for representing data, such as object stores and others. So this is again going to be connected to what we covered in the previous lecture. And now we are moving towards a little bit starting to merge the theory and the practice, such that you can start to understand why all this nomenclature and all these different concepts may come in handy when you're designing your database, your own databases. So here, the relational database is just a set of relations. And in the previous lecture, we said that a relation is essentially what you think of as a table per se. But more concretely, it is made up of two parts. So you have the instance, which is just the table with the rows and columns. And the number of rows in a table is called its cardinality. That's one thing to remember. And the number of fields is called the degree of the table or the instance. And then that's one aspect of the relation. The second is the schema. So we talked about schemas in the previous section. That the schema really tells you the name of the relation plus the name and the type of each column. So you can think of a student relation or a student schema as having the name students, and then it has a number of attributes like the name, which has been specified to be a string. You have the login, maybe that would be like the username, which is also a string. And then you have, so first was this student ID, which is also a string. So you have the student ID, which is a string, the name, which is a string, the login, which is also a string, and the age, which is an integer, and the GPA is a real number. So it's essentially a floating number. So again, just to remind ourselves, the relational model gives us a way of representing our data using this in terms of relations, where relations are made up of these instances, where you have your rows and columns, and then the schema kind of defines the structure. So you can think of the schema as defining the structure, saying that the table will be called student, and it can take any student ID that is a string, a name that is a string, and so on. And then the instance is an instantiation of this, right? So if, say, you have a table of students in the biomedical engineering class, so that would be an instance of this relation, or also an instance of this schema that is represented here. So the schema is the definition, and the instance is the actual data that goes into the table that is a part of your database. So you can think of a relation as a set of rows or tuples where all rows are distant. We'll come back to this in a bit. So again, this is an instance of the student relation. As you can see, the important thing is that you have your columns here, and then you have the data, which is represented in rows. Okay, so this would be the student relation. And relating back, the cardinality is 3, because we say the cardinality is the number of rows in the relation, in the table, whichever way you want to look at it. And the degree is 5, because the number of fields is 5. Okay? So the question for here is whether all columns in a relation instance have to be distinct. The answer is of course yes in that case, in order for you to be able to differentiate between two different columns. Otherwise, you wouldn't be able to say these two fields were called name. It would be hard to figure out which of the two is which when querying for information. Now, that is about the structure. One of the major strengths of the relational model is that it's very simple. It supports a very simple querying language. So it's very easy. So if you store your data in a database that is making use of this relational model, it has a very powerful querying language. So querying is essentially ways to ask questions from your database. So let's say, and again, we are going to look at some more complicated examples. So I'm seeing comments about the network not being good. Okay, let me try to switch to another network temporarily. Right, is this a bit better? Okay, let's try to carry on. So I'm going to do, if this starts breaking again I'm at campus, so you know how that can be. If this starts breaking again, then we can decide I could just record the lecture and upload it instead. But for now, let's try to continue and see if this works out. Okay. So like I was saying, say you had this table in your database, and you wanted to find out which student is aged 19, right? So asking, oh yeah, and someone is talking about a physical lecture. Is everyone around? So I think are you all in the same classroom or what's going on? Not today. So I think what we will do for next week, we will have the lecture physically on Tuesday afternoon, since you're all around. The Tuesday afternoon, we can have the 2 to 5 lecture in person. Okay, great. Okay, let's carry on for now. So if you wanted to find out which students are aged 19, so asking a question like that is what we call querying the database. So, and what we were saying is when using the relational model, it has a very powerful and simple way of querying the data. And that is one of the reasons you'll find the relational model is one of the most widely used models for representing databases. And so you can write queries intuitively. And again, we are shortly going to start looking at some examples of queries. And then by the end of today, there is a course, kind of a practical course on working with databases that I'm going to sign all of you up for. I obtained permission from the creators of the course for this, such that you can get you can get hands-on with querying data. So I'll make sure you have all signed up on the course websites, because I'll use your email address that you used to sign up on Mwele to register you for the other course. So that's a very important thing. So make sure um, you enroll into the course on Mwele, such that I sign you up for the other course, since you need to complete all the assignments in that course in order for you to receive a grade for that exercise. For essentially the practical sessions to do with relational modeling will be covered by that small course. It's not a very long course, maximum 4 hours. You should be able to complete it, but I'll give you up to 4 weeks to make sure all of you can complete all those assignments. And again, you'll be getting notifications for that in your email if you have signed up on Mwele for this course. Okay, if for some reason you can't sign up for Mwele, just let me know, then we can see a workaround for that. Great. Right, we were saying that when using the relational model, queries can be written very intuitively, and the DBMS. So remember, the DBMS, it's that software that enables you to efficiently manage databases. So think about it as your database. The database is the collection of data you care about for a certain purpose, say for modeling what happens in a university or a school, and that database is managed by this DBMS software. And that database, if it conforms to the relational model, it makes use of these relations. Or later you start just getting used to calling them tables. But for now, it's a good idea to just keep the correct naming for this. Okay. So here are the keys that the relational query language has very precise semantics for relational queries. We're going to look at those shortly. And also importantly, it allows the optimizer to extensively reorder operations and still ensure that you have the best answer. So when you write a query, you could, and again, you're going to start seeing this shortly, that there are many ways in which you could query for data from a database, and some of them may not be very efficient. But because you're making use of this relational query language, the DBMS can go in and optimize your queries for you such that they run as quickly as possible. So these relational database management systems have those built-in optimization mechanisms that just take your query and figure out the best way to run it for you such that you get your data out as quickly and as efficiently as possible. So, and this leads us to the SQL Query Language. I'm sure a number of you have heard of this, and this is the most popular relational database query language, and will be the focus of most of the practical aspects of this course. At least for the SQL sections of the course. So developed by IBM, been around since the 70s. And there's of course a need for standards, as you'll find with so many of these database and programming languages. There's a need for standards because each maker of a DBMS will try to have their own implementation of the query language. So if you do not have standardization, there will be mass confusion. It will be hard to interoperate between different providers. Even the developers themselves or the database administrators will be very confused if you do not have the standardization. So as of a number of, I think this is probably a decade. I'm not so sure if there's a newer version of this, but you can check. But these are some of the standards that have been around for a while. But this SQL is a pretty stable language, so it doesn't change so much over the years, which is also a very good thing because then you know it is reliable. You will not have features that break a language. Maybe you write a query today, and due to a change in the standard, it doesn't run anymore. That doesn't really happen with SQL because it's a fairly stable language. Now we can start talking about the queries, and again you're going to have an opportunity to do all this on your own in a practical setting once you have enrolled for that practical course. So if this is the table that we have, again, this is just a subset of the table. You can imagine if you have all the students in the university, I don't know how many, I think currently there are about 30,000 students in Makerere. Then you'll have that many rows in a table like this. But here, just to demonstrate, we are just using a small subset which can fit on a page. So if you want to, so let's say your query or the question you want to ask of this table in the database is that I want to find all the 18-year-old students, right? How can you write an SQL query, right? So the statements you write in the SQL language are called SQL queries. So, and by far the most common one you'll find is this select statement. Okay, so here, to write this, to convert this into a query, you write select star. And again, we are going to go back and explain what this star means, every part of this query. From students, there's this S here. Not always necessary to do this, but again, I'm going to explain why it is here, where s.age is equal to 18. So let's break it down now. So select star. So whenever you have a select statement, what goes next to it, typically, in almost all cases, are the names of the columns that you want to return from your query. So if you write this asterisk here, it means that you want the query to return to you all the columns, right? So it is essentially saying select whatever you're returning, show me all the columns, right? From students. So this table or this relation is called students. So in the database, each relation or each table has a name. It just so happens that this particular one is called students. So essentially, like English, I'm saying select essentially all the columns, and of course, this query returns rows. So select data from the database and give me back all the columns from the students table, because a database can have many tables, but each of these tables has its own name. So you need to specify from which table or tables, it could be one or more tables, you want to return the data from. So in this case, we are saying we want the data to come from the students table. And finally, you can have a condition. So this condition is optional. So for example, if you just stopped here, a select star from students S, it will give you back all the data that is in the students table, right? If you stopped here. But because we have this extra predicate where we are saying that we want only the students that are 18 years old, then you need this extra where statement that is saying where s.age or student.age is equal to 18. And I think now you can understand what this S is for. It's just an alias for the student's table name. So it just makes it easier for you. Like you just have to write less characters. So it's kind of saying that from students S, which you can also call just S in this query, right? Where student.age, now this S is just a proxy for students. It's the same thing. You can write students.age or you can write s.age. Of course, you prefer to just write s.age because it's shorter. So now you have the complete query. So essentially, I should say this query here is running off this table. So that query was running off this table because remember here you also had a student that was aged 19 years old. But after that query, we only get back these two rows because those are the ones that have students that are aged 18. I hope this is clear. So, but I think you have to agree that it's fairly intuitive as a language compared to all any other languages you've encountered. It's quite easy. It's almost reads like English. Like, give me back all the data, including all the columns from this table called students, and only give me the rows where the age of the student is 18. So you can literally just read the SQL language as an English statement, which makes it quite easy. It can, of course, get complex depending on the complexity of your database, but for the most part, it's very easy to understand what's going on with your query. So one other thing, like I told you, if you write the asterisk here, it gives you back all the columns. So if you wanted to have only specific columns, then you can specify which columns, only the columns that you want. So let's say in this case, we only wanted to see the name and login, for, say, a certain system, maybe for AIMS. You can just put s.name and s.comma, s.login here, then it will just give you, just data from these two columns. Okay. Right. So, and like I said, so that's it. That's it for a simple introduction here. But you can only also query multiple relations, right? So this means that, of course, since our database is not so straightforward, or our database design is in such a way that the data is stored in multiple tables. We've been talking about the students table, but we can also have an enrolled table. So where the enrolled table is essentially is telling us which student is enrolled in which course and what grade they have. So if you go back, let's see if this is a one-to-one here. So you can see each student has a student ID. This could be like the same as a student ID, their name, the login for an account, the age, and the GPA. And then we also have this table that is telling us for each student ID. Of course, this is the enroll table, which has all the information about enrollments in courses. Of course, you do not need to repeat all this information. The point is that if I know the student ID, right, that's sufficient information to let me know who the student is. So if I'm looking at the table for enrollments, I don't need to repeat all this information. I just need to bring the student ID, which will represent the student, and then the course ID, which is written here, and then we can have the grade, whatever grade the student obtained. So if I want to, if we look at this query and we try to figure out what's going on, it says that we are returning s.name. So we look here and we see that S just stands for student. So we have demystified the first part, that we want to get back the student name. And then E.cid, and we can see E is the enrolled. We are pulling data from the enrolled table, which is essentially this table, right? And from this table, we want E.cid, which is this course ID. So it kind of looks to me like we are interested in seeing student names. Someone is requesting for the lectures to be uploaded. Of course, the lectures are being recorded. I hope today's lecture is being recorded. Yes, I'm going to upload this and the previous lectures were right after this. Thanks for the reminder, Rogers. Right. So where were we? So we are interested in the name and the course ID. And this information is coming from the students table and the enrollment table, or the enrolled table, right? But of course, we need to find a way of connecting these two pieces of information, right? So if we want to see the courses in which each student is enrolled, we need to make sure that the course IDs that we are seeing here are only for that student. So we go and check for only the places where the student ID, this ID, is the same as the ID in the enrolled table. So essentially, you're saying that the ID for the student is what is uniquely identifying them in the enrolled table. So we are just pulling out the records for each student, whereby essentially we're pulling out enrollments that only apply to that student. So, and we do that for each of the students. Okay, and there's an extra predicate here, an extra condition, which is telling us that the grade in the enrollment table should be A. So essentially, if you put all this together, the idea is that we are trying to pull out, to get the name and the course ID. As you can see here, this is the result of this query. So we are trying to put out the name and the course ID from the student table, or data coming from both the student table and enrollment table. And this just makes sure that we are only getting information that rightly corresponds to each student. So we are enforcing the fact that the student ID here should be the same as the ID that we are seeing in this enrolled table, and that the grade should be an A. So if we look at the table, first we can even start from the end. Like where do we see an A in the enrolled table? And this is only appearing here. So this is the column we care about in this case. And we're picking out the course ID, which you can see here. And then we need to find which student corresponds to this student ID, this 53650. So we go to the student table, and we can see that 53650 corresponds to Smith as the name. And if you go back to the table, you can see that the name that came out is Smith, course ID, and the grade. Okay. So as time goes on, you will get used to kind of thinking about these queries. But most important here, we've shown how you can go about querying for data that is spread across multiple tables. Okay, so that's a little bit about querying. So how about creating tables or relations? So again, this SQL language is very versatile in that it gives you a way to both query data and also to create the relations or the tables themselves inside the DBMS. So exactly same language, it's just different statements that you use. So in this case, we're going to talk about how to create relations first. So the idea, again, is this is the statement right here. It says create table students. So it's telling us to create a table named students, right? It's almost like we're trying, this would be the statement that created this table that we've been looking at. So we are saying create table students, and then you open this bracket. So you're done with the name of the table. The next thing you need to define the fields, okay, the different columns in the table. So the first is, so for each of them, you need to specify a name and the data type, okay? The first field in this case is the student ID, and we are saying it takes up to 20 characters. These are string characters. Okay, so that's the first one. Then we have name, another 20 character string. Login, we have decided this time to only have 10 characters. And then age, which obviously should be an integer, 2, 10, 50, whatever. GPA is real, and like I said, this is a float because your GPA can have a decimal 0.3, 0.4, 4.8, or whatever you have. So essentially, this is how you go about creating a table, and you can see this is kind of the process of defining the schema for our table, the name and the different fields or columns that we have in our table. And again, this is a very intuitive statement in the sense it's telling you create a table that has these columns, each of which has a defined data type. Okay, and this is how you go about creating the enroll table, which only requires the student ID, course ID, and then the grade, which in this case we decided to put as a 2-character string. Okay, so this is how you go about initially creating the tables, these two tables that we've been looking at in a DBMS. Okay, so of course, at this point, there is no data in the table. So you've essentially just defined empty tables, and then you have to use another mechanism that will look at data to load data into the database, into the tables. Please remember, if you have any questions, just post them into the chat window. I'll be happy to answer them at any point. Okay, so we now know how to create a table. So how do you remove a table from a database? And that's also easy enough. The statement is drop table, then the name of the table you want to drop. It's that simple. So the capitalization is important. Don't forget this. So if it says drop table, it really means the whole thing is in caps. The same thing with the create table, the same thing with everything that you see capitalized here. It's a convention. If it's lowercase, it might work, but it's always, in some cases, some databases enforce this, others don't, but it's a good practice to get used to just capitalizing the keywords that are coming from the language. Okay, so drop table statement destroys the relation student or removes that table from. And this is again what I was telling you, that when you start looking at SQL, they just switch back and forth between relation and table. It's essentially the same thing in SQL. So it destroys the relation students or the students table in the database. So it essentially blows away everything. Like it will delete the table and it will also wipe out all the data in that table. So you kind of need to always use this very cautiously, because there's no way to recover the data once you have run this command. Okay. The next thing is, say we created our table, added some data, and then found out that we need maybe to capture the student's height or something like that, right? So we need a way to add the code that will take the height data, and the way you do that is by using this alter table statement. So again, it's almost pure English. Alter table, the name of the table, student, and then you say what alteration you want to make. So in this case, you want to add a column that is called first year, and then you specify the data type that will go into that. Now, one thing that you find in some cases is that, or if you think about it correctly, so when you're adding, so someone is asking about a tuple. So a tuple is essentially a collection of values, right? So if I write this, what I've typed in the chat window, that's essentially a tuple of two values. So and it can be any number, 2, 3, 5. It can even be a mixture of different data of different types. So the way, whenever they refer to a tuple in regards to a database, just think of all the values. Just think of a row essentially. That's what you typically refer to. So this row, these values, the values in a row of a database are a tuple essentially. But it can be used in other contexts as well. And here, so here when they say we are dropping the schema and the tuples, we are essentially meaning that we will delete the structure of the table together with all the rows. So you can think of tuples as rows in this case, together with all the rows in the database. Okay, I hope that clarifies it for you, Andrew. Right. So we know how to create. So as I was saying, if you're adding a new column, if you think about it, if you add a new column, that new column, you're only making a change to the structure. So if the table already has data in it, it means you're now going to have a whole column that has no data in it. So one way of doing this is that you can first fill all values with null, and then you go back and populate them with data. once you start doing it, you will see this. So, okay, you have, let's say you have your list of 40 students in computer engineering. You have all their data, GPAs and so on, and then you decide um, uh, you want to capture, say what else, their hobby, right? So if you run this statement on the student on that table and say add column hobby and maybe character 40 or something like that, some string, it means that you have changed the schema, but this new column that you've added does not have data in it, right? So what you can do is you can temporarily, or the database will automatically do this for you, is that it puts in a null value everywhere, and then it's your responsibility to go in and for each student um, add the correct value for that student. Again, it will become clearer as you start working with this. So the missing bit of this is how do you get data into the database. So you have created the structure using this creation statement or DDL statements, like they call them. So how do you get the data in? And again, it's quite simple. You just write the statement insert into, and then you specify which table you wish to insert the data into. And then you would have, in the case of the students, like you can imagine, we define the schema for the student, all the different columns. So you need to provide a value for each of these different columns. So in this case, insert into the students table, then you specify the fields in brackets, then the values, then you just have another the row that you'd like to insert into the database. So it does the one-to-one correspondence. So the value for SID is this, for name is this, for login is this, for age is that, and so on. So again, a very simple, very straightforward statement that you can use to insert one row entry into the database. There's a variation of this, of course, that will let you insert many rows at the same time into the database. Okay, so, and that's it with inserting. You can also delete tuples satisfying some condition. So again, when you see tuples, you can in your head just substitute it with rows, like rows in the table. So you can also delete rows. So in this case, we are not deleting the whole table. Rather, we would like to delete just some rows that satisfy a certain condition. So it's kind of very similar to the select statement. So actually, typically, how I deal with a deletion, I first write a select statement, right, and then it pulls back the data. Then I just replace that first select section with delete, right? So here it is saying let's delete from the student table whichever student has the name of Smith. So again, quite straightforward, right? The action, where the data is coming from, and then the condition, and then this will pull out just those rows that satisfy this criterion, and then you will they will be deleted from the database. Now, again, this is a very dangerous statement. So when you're writing a delete statement, I would say always write the condition first if you can. Because if you forget this condition, this where clause, I, I think you can imagine what's going to happen. It's going to delete all the records, all the rows in the students in your table. So this again, like its counterpart that drops the whole table, should be. Okay, I think I dropped off for a second. Um, what I was saying is that you need to be very careful when making use of these delete statements. Otherwise, you can do irreparable damage to your data set. Right. Right. So, and that's it. So, for the most part, the statements we have just gone through are the bulk of the statements you will need to create and do routine tasks on your data on your database. Okay. So the other thing that that is important to discuss are integrity constraints. So an integrity constraint, again, will be very clear shortly. So it's a condition that must be true for any instance in the database. So you can think of integrity constraints as checks, kind of like validation rules or validation checks you put in place to make sure that there is no strange data or data that does not conform to the way you expect inside the database. So there's some, so you specify these constraints when you're defining the schema, and then there are also checks when the tables are modified. And then we'll see what this just statements mean. But this just essentially means that if you want some constraints enforced in on your tables, you need to specify them when you're creating those tables. So essentially, these statements do not have any constraints. So essentially, you could put, for as long as you have the correct data type, you could put anything inside here. But if you want some kind of stricter control for the kind of data that is going to come into to go into your database, you can make use of these constraints. So maybe a very simple one, just if this all seems abstract. Let's say on this table we had a field for the registration number, right? So you could just make it a string, right? But that means that someone can put anything inside that field, right? Which is probably not what you want. Like you want to be able to check that the registration number that is coming in is properly formatted, right? So what you would do, you'd have an extra constraint on um, the registration number field that checks that it is correctly formatted with the 2 slashes and so on, numbers, letters, then numbers at the end, such that if someone puts in a registration number that is not correctly formatted, the database is not going to accept it. So, and again, that's why you call them integrity constraints, because then they make sure that whoever is using the database uses it in the way that you expect them to. Otherwise, the applications that use the database might end up with stale data that does not make any sense. So again, that's why it's these constraints are very important to know. So this says the legal instance of a relation is one that specifies all the specified um, integrity constraints. So the database will not allow illegal entry. And then it also helps you to avoid data entry errors. Again, as we were discussing, that the database will not allow data that violates any constraints that you have defined at creation time. Okay. One of the constraints that you'll find is the primary key constraint. And this primary key constraint, it could be one or two fields on in your database where you say that no two distinct tuples can have the same values in all key fields. So the point is that an easy one is, let's first consider the case where you have only one of your fields as the primary key. For example, if you are looking at this table and you wanted a field that uniquely defines each row, I think an automatic candidate would be the student ID, right? So when you're defining your table, you can specify that the primary key for this table is the student ID, because you're sure that it's never going to, or it must not be repeated. Not two students should have the same student ID. So it's a very good choice for the primary key. So essentially, if you define the primary key on your database, the database will automatically enforce for you that if someone tried to insert another student with the same student ID, the database will immediately reject that, right? And this is again what you expect. You do not expect to have two students who have the same student ID. The system would not be able to resolve that. So the best way is you put a constraint such that if it happens, it's immediately rejected by the DBMS. So, and it's also in some cases you can have two fields defined as the key. That has some extra meaning to it. But if you have two fields, let's say if you have two fields that you want defined as the primary key, then the idea is that the combination of those two fields should also occur only once. Okay? So, but internally, the database will select one of them to be the primary key. But the point is that, say you, so if you're looking at your table and you want to choose what primary key to use, for example, would name be a good one? Obviously not, right? Because you can have two students with exactly the same name. So that would cause problems for you. Whereas for the student ID, you'd be sure, excuse me, you'd be sure that you only have one of those, so it's a very good one. Okay, and then here we see student ID, GPA would be a super key, for example, whereby it is made up of two fields, and anyway, you only have one of these, so this other one doesn't even matter. This is enough to enforce the primary key relationship. And then you have the concept of primary keys and candidate keys. you can have many candidate keys. By candidate, it's essentially referring to the fact that there could be another potential primary key. So for example, for this enroll table, we are saying that the combination of the student ID and the course ID is the primary key. So this is essentially enforcing the fact that for each student and for each course, there should only be one entry. Okay, and you can see the value in having a primary key that is made of two fields. For example, if you said that only the student ID is the key for this enrollment table, then it would be very possible for this course ID to appear many times since you did not put any restriction on it. But because you know what you want, that you really want for each student and course ID to only have one entry for the grade, for example, then you need to have a primary key that is a combination of these two fields. And again, as you do more and more examples of this, you'll start seeing how to select your keys given the domain that you're trying to model. And then, yeah, and I mean, if you want to have extra keys, you can specify them with this unique constraint. Okay. And then foreign keys and referential integrity. So a foreign key is really a set of fields in one relation that is used to refer to a tuple in another relationship, or a tuple, however you want to pronounce it. For example, I think this will be easier to show here. If we are in this enrolled table, then this SID is a foreign key, right? So it is a primary key in the students table, but because it is used in the enrolled table, it is referred to as a foreign key. So essentially, a foreign key is a primary key of another table that appears in another table, essentially. So the fact that you have this student ID inside the enrollment table, and we know that this student ID is a primary key in the students table, that makes it a foreign key inside this table. And the point of having foreign keys is that you can use them to point to records in another table. Okay, so if I'm here and I see this student ID, I know that I can go to the students table and find out which exact student it is. So that's the whole concept of a primary key, if it's the main unique key in the table. But if that key appears in another table and it is being used to refer to the data in its original table, then you call it a foreign key. And of course, it's obvious to see why you do that. It helps you to avoid the duplication. For example, in this case, you'd have to write if you do not use this key, you'd have to write down all the information about the student here. Whereas if you can just use the key, the foreign key, you have the connection between this table and the other table, and you can, for example, use a query like this to extract information about the student name and everything else you need from that respective table. So that's foreign keys. So referential integrity essentially means all foreign key constraints are enforced. So it essentially means that if we are in this table, we cannot allow a record that does not have this key, this foreign key. If you're enforcing referential integrity, it means that for each record in the enrollment table, there must be a um, student record, or there must be a student ID that is entered. For example, if you try to enter a course like chemistry 325 with a grade of A, but you did not provide a student ID, this database will reject it if you enforce that referential integrity. The referential integrity means that the foreign entity or the foreign ID must exist, otherwise the record will not be allowed. So you can see how that is valuable. It stops you from having enrollments that are not attached to any students, right? So if you enforce that referential integrity, it makes sure that you do not have any dangling enrollments that are not attached to students. Right, perfect. And then again, this is what we're talking about. So, and if you wanted to, and this is how you define that foreign key relationship. So when we are creating the enroll table, we know it has a student ID, a course ID, and the grade. Again, we said why we need a primary key of student ID and course ID, because we do not want the combination of the student ID and the course ID to appear more than once, right? And then we have to say that the student ID is actually a foreign key, right? Coming from or referencing the students table. So once you change your creation statement like this, it means that you have in effect enforced the fact that any student ID that shows up in this enroll table must actually have come from the students table. So it's a way of making sure that someone does not come in here and just punch a random number, maybe 223 for the student ID. But rather the database will check that, okay, you're saying you're entering an enrollment for student 53666. Okay, let me first check the student table and see if they exist. If they exist, then the transaction proceeds. If that ID does not exist, then the database is going to reject that entry. Okay, and that is what referential integrity is. It makes sure that the relationship between two tables is enforced such that you do not end up with dangling references between tables or a database that is in a state that doesn't make sense. Okay, and then if you read this, you'll find that this is just explaining what I was just saying. And of course, the other advantage is that it gives you a way of detaching updates. So if I wanted to change maybe the GPA of this person, right? I do not have to mess with the whole database. I can just do it locally and it will still be the same student that is referenced. As opposed to if I were just copying this record and putting it there. I would have to find this record in every place. So for example, you can see that this student 53666 appears 3 times for these 3 different courses, right? But each of them is referring to the same Jones person. So imagine if we did not have this, we would have to copy this information in all these places. So if that GPA changed, we would have to change it for each of these entries. Whereas if we are using this foreign key relationship, we can just change it once and all the records will be updated with that information because they are only keeping the reference, they are not keeping a copy of this information. And that is the reason why this is a very powerful tool. The foreign key is a very, very powerful tool. Okay. The other thing to consider is what happens when a record is deleted. So you have two options. You can delete all the dependent items, or you can set to a default value, maybe null or something. Okay. So what does this mean? So imagine we have this table that has this relationship enforced that all students in the enrollment table, you can only have records for existing students. So say if you deleted this student, you have to specify what you want to happen, right? You can decide that if I've deleted this student from this database, I should delete all the enrollment records because anyway, it's meaningless to have students. I mean, to have enrollment records that do not reference the student. So that's one option. The other option is you could select some default value, maybe say -1 or something like that, such that whenever a student is deleted, you just change the ID to that, such that you can keep these enrollment records, but now they do not refer to any student. And that choice is really up to you. And this is how you can go about um, making a statement that determines that. And of course, all these integrity constraints come from the domain, right? You have to decide for yourself, if I'm building a database for the university, what do I want to happen when a student record is deleted? Or do I even never want that to happen? Because that could be another thing that you can enforce. Say I never want anything to be deleted. There are ways that you can do that. And then the final concept is a view. So a view is essentially just a snapshot of your data. So say in this case we want a view, we want a view or a way to return all young active students, the names and grades of young active students. So we can create a view. In this case, it's encapsulating this select statement that is selecting the name, the grade, similar to the query we wrote before. And active, we are saying if they are less than 21, they're active students. So we have created this view. So the difference between the view and a table is that a view does not actually have any rows in it, right? It's essentially, it calculates the rows or the results when you call it or when you run it. Okay, so a table, remember, physically stores the data you put in it, whereas the view just pulls out that data when you access it. So, and you can see the advantage of creating views. So for example, here you can encapsulate a query, maybe it's a query you run all the time, into a view such that you can just call on this view and it gives you back the results. And of course, another thing it can do for you, let's say you change the name of this enroll table, right? Your view wouldn't break because the interface to the view is still the same. You just call young active students. But here you can just change the name to enroll students or whatever you change it to. And it would still work. It would still work just perfectly. Okay. And of course, if you drop a view, the other thing is that since a view is just kind of a snapshot, if you delete a view, it has no effect at all on the schema and the data set. Okay, so just think of the view as if I have some complex query that I run often, or if there's a way I want my data returned that is different from the structure that is in the database, then I can make use of the view to do that. Okay, and then a view, there's a security aspect to them because a view is just a presentation or a summary of the data, so it has no access to the underlying data. So if someone were trying to hack your database, a view would be completely useless to them, rather than if they had access to your full students' database. I know we have reached 1 o'clock, but let's just do 5 more minutes so that we can wrap this up. The other thing to think about is, remember we were looking at the logical conceptual design. We are looking at those entity relationship models. You should be able to look at an ERM model and think about the SQL you write to create that table. For example, here we can easily see that the name of the table is going to be employees. It has 3 fields. This one is going to be the primary key, since we have this underline. So we have SSN is a character field, and C we have specified it here as the primary key, meaning that it should be unique for each of the employees. Then we have the name, which is a character field, and then the note, which is an integer field. So you should always be able to read these ER diagrams and figure out what SQL you need to create. Right, and of course you need to be able to again read ER diagrams that are like this and kind of think of the way you create a table for that, and also taking into account these relationships if they happen to be used. So in this case, you can see that you need one table for employees, you need one for departments, you need another one for managers, and then you need to enforce the fact that you're only allowing one manager for each department, because this is what this information is telling us. Okay, and this is how that will translate. You have your managers here. Of course, it has to reference this and this, those 2 keys, and you can see them here as foreign keys. And the department ID, we have chosen the department ID as the foreign key in this case. I mean, as a primary key, since we only want one entry for the department inside the manager. So in a way, you're kind of enforcing the fact that you have one manager for the department. And again, as you do more of this, you get used to it. Again, you can look at all these other different examples here, just to get used to how you can deal with converting ER diagrams to SQL. This is another example. Remember, we looked at weak entities. So weak entities only exist in the framework of their owner entities. Like we talked about policies and dependents. For the dependents, they only make sense within the policy. So for example, if I deleted the policy, it should always be that I delete all the dependents that are attached to that policy as well. Yeah, this is translating hierarchies. Not so important, but again, you can take a look at these examples and try to see. They are very well written and explained, and try to see if you can follow what procedures they are taking to translate these ER diagrams to full SQL statements or into databases. Okay, and then summary. So the relational model really represents data in a tabular format. It's quite simple and intuitive, and frankly the most popular and used approach. And then you need to know about integrity constraints that ensure that we have the clean data in our databases, and our database management systems always check for integrity. They always make these integrity checks. Primary keys, very important. They make sure that all the rows in the database are unique. And foreign keys give you that way of pulling in data from or relating to data from another table. And then there are also other domain constraints, like we talked about, say the manager's constraints and so on. There are also constraints that you can do. Let's say you can say for the age field, I will only allow between maybe 15 and say if you're looking at mature H entry, I guess you can say I only want between 35 and 80 or something like that. So you can write a constraint, and the main constraint that enforces the range of values that are allowed in a particular field as that. And then it's a very powerful and natural query language. And the fact that you can study the rules, or there are rules that can help you to translate an entity relational model to a relational model, or that can take you from a figure to an actual database design. And again, more of this you can read about in the book. Yeah, that's it for the lecture today. I'm going to upload the videos as soon as I'll upload this first, then I'll upload the other one later, as soon as it finishes saving to disk. Otherwise, thank you very much, and enjoy your weekend.